Here's a few news articles. This one, I'm not quite sure what to make of. This guy claims that he has destroyed RSA, but he spells the word destroys wrong. And I downloaded the paper, and the paper is just page after page of mind-boggling, dense mathematical symbols. So I certainly cannot decide whether it makes any sense or not. This guy is apparently a real cryptographer that's been around for a while, so maybe he really has. His claims he makes here are quite good, that he can break a 800-digit RSA key in 10 to the 10 operations, which is not very much at all. I mean, a normal processor does more than 10 to the 9 operations per second, so this is very much achievable. So if that is true, then he really has destroyed RSA. So, and that's the point, faster than the previous quadratic sieve and number field sieve, which are the fastest routines before. So this is what we've been talking about for decades and really centuries, is that maybe someday somebody would find a smarter way to factor numbers, and if they did, that would destroy RSA. And this guy certainly claims that he has done that thing, which people have been looking for at least 2,500 years that we know of. So anyway, it's very interesting, and I'm waiting for people to digest this and publish more accessible commentary on it from experts so they can decide whether he's really got it or he really hasn't. But if he's really got it, then that's the end of RSA, even if we don't have quantum computers, as he says. So I mentioned in various other places the CPAC is quite notable. This is the heart of the Republican Party, the Conservative Political Action Committee, and they made their stage like a Nazi symbol. And somehow it's not showing up here. This thing is blocking the pictures for some reason. Let's see if I can get it to quit doing that. Nope, looks like I can't. Anyway, for some reason the picture you need is not showing up here, but it's the stage underneath his feet is designed as the official symbol of the Nazi Party. It used to be a swastika, but they changed it to a different rune, which the Nazis also had on their uniform, and that's impossible to believe that's a mistake. And even when alerted of it, and even when Hyatt was going to be boycotted to punish them for openly supporting the Nazis, they didn't do anything about it. So there have been a lot of call-outs to the Nazis and white supremacists, dog whistles they call them, where Trump supports them but tries to not quite admit that he's supporting them. And this is the most open, making it extremely clear that at the very heart of the Republican Party, the people in charge are Nazis and closely in bed with Nazis and allied with Nazis, and they want to make sure the whole world sees that, and then they want to pretend to deny it. So I think we've all seen this. It's been incredibly obvious. His Yodel rune, that's the name of the thing, yeah. And there used to be a good picture where you could see it, but somehow I'm not finding that picture on this page. Anyway, so this is pretty notable, and I've been thinking, it's impossible to overstate the danger the United States is in now. The Republican Party now embraces complete lies, violent overthrow of the government, complete disregarding of the votes. They don't even care who wins the election. They're just going to take it by force anyway. And now open white supremacy and Nazism. This is just what happened in the 30s in Germany. It is impossible to overstate the extent to which the United States is being destroyed from within. And that's why I hope that the Biden administration has the guts to kill the filibuster and make big changes, because if they don't make big changes, this will not be, I don't think there will be another election. Trump has lived up to the absolute worst fears very nicely. And here's a student sent me this. Maybe this is one that has the picture. Nope, doesn't. Okay, I don't know what this one does. They apologize for the obvious. Yeah. Oh, the refuses to apologize. Yeah, that's it. Yeah, so I mean, it's been the case that the Republicans are very, very racist, especially under Trump, but they used to make some pretense of trying to hide it and be subtle about it, and now they're just openly making it obvious, which makes me think that they no longer feel like they need to hide. They no longer feel like there's a risk. So I think what's going on is they think they can just come out openly. Yeah, link to the picture. Well, I went to that page and the picture was not there. Anyway, 50 votes needed to end the filibuster, not 60. But there are two Democrats that currently refused to block it. It's at the top. It wasn't at the top of that page when I opened it. I'll try it again. I open the page. Nope, there's no page that appears on. There's no picture on this page. Oh, there. Oh, that's it. Thank you. Good. Yeah, there it is. And there it is. Yeah, that's it. I've covered it with text so you can't see it, but it's on this guy's color. There it is. That's the shape. It's not something that would happen by accident. Thank you. Anyway, the Canvas APK shows 49%. I have no idea what that means. Does it include the extras? Okay, I don't understand any of that. Canvas APK? You're downloading a Canvas Android app and analyzing it somehow? I need more information to answer that question. Anyway, maybe after the lecture you can maybe share your screen with me and show me whatever you're looking at, because for the assignments and projects. Oh, I think I know what you're talking about. In Canvas, this is a good thing to point out. In Canvas, it doesn't know what extra credit is. So it makes you think you have a low percentage when you don't. The only thing that matters is the total number of points you make. And I can't get Canvas to stop displaying a wrong percentage. So just ignore the percentages in Canvas. Good. Now I think I figured out what you're talking about. This site was hacked with a lot of SQL injection. Oh, the Gab. Yeah, Gab was hacked with SQL injection. Yeah, it was. In fact, I think I've got that somewhere here, and I guess that'll be the last one for today. Yeah, for this one, Gab was hacked by SQL injection, supposedly 70 gigabytes of data, although they haven't dumped it publicly, but they're supposedly going to dump it to researchers and journalists, so we may be reading articles about it. Gab was the third far-right place they went after they got kicked off of Twitter. Then they went to Parler, and Parler was hacked and went down, and now they went to Gab. Yes, you can detect SQL injection, but only if you have configured your systems to make good logs. And typically they haven't. Oh, Clapper's the new one? Okay. Yeah, they have to keep running from site to site, which is why the Republicans complain that they're being censored, because they keep setting up neo-Nazi sites and having them taken down. I know they can't get on the mainstream news anymore, because all they'll do is like say Trump won the election and the election was rigged, and nobody wants to be liable for the consequences of publishing that information. It's like that Pillow guy. Can't get on any mainstream source anymore, because if you let him talk, you'll get sued, because he just lies. So they have to keep coming up with special places where they think they can lie all they want, although I think they'll probably all just get sued too. Anyway, all right, so we're up to the official time here, and I got a lot of stuff to show you today. This is 126, and the first bit is to talk about OllyDbg, where we'll do a few more things than what we did before. And then I want to show you PMA 122, which is using the Windows 10 based Flare VM. Yeah, right-wing TikTok. Yeah, yep. They got a bunch of them. Yep. Anyway, so let me find my slides, which should be, that's right, same old issue always happens. I update them and then I have to close them. So it's File, Chapter 9. All right. Good. All right. So OllyDbg has been around for more than a decade. It is the favorite of hackers and gamers all over the world. It's a great reverse engineering tool, great for beginners with reverse engineering, why we're starting with it. OllyDbg 1.1 was purchased by Immunity and rebranded as the Immunity Debugger. So the Immunity Debugger is almost exactly identical to Olly, except it's still being maintained and updated. So Immunity is probably a little better than Olly, and you can do everything the same thing in both products. About half of my projects in various courses use Immunity and half use Olly, and there's really no big difference. Now, OllyDbg 2, when I tried it, didn't have these features, these functions, N2HL and N2HS, and so I thought it was broken. A student emailed me and said they're actually in there somehow, hidden as sub-functions of one of these. So technically, OllyDbg 2.2 is not completely broken, it's just more confusing. And it didn't seem to have any valuable new features, so like most people, we just stuck with OllyDbg 1.1. The big problem with OllyDbg is you can only do 32-bit apps, not 64-bit apps. Anyway, so You can load an exe directly in OllyDbg, which is what we did last time for things like Putty and some games that were command line terminal games. You can also load a DIL directly into Olly. It will use load_dil, the Windows feature that is there just to load DILs. And you can also have something already running and connect to the running process. You're attached to the process. That's all debuggers can do that too. That's another way to go. So you just open this thing and it will load it into memory and stop. Now it'll stop at the entry point if it can find it. If it can't find it, it will go for the entry point in the PA header. Much more about that later. Every file has a header, and in a portable executable file header, it has a starting address. And it can stop there. And as we saw, when you're running 32-bit programs on 64-bit code, it stops at some funny place having to do with Windows launching the Windows subsystem on Windows, and you have to run it once to get down to the normal starting point. You can attach to the running process, then it will pause the process and stop it while it's running by, and you'll end up somewhere in that process. All right, and you can hit Control F2 to reload the executable. F2 sets a breakpoint, and these key presses that might seem pointless are in fact extremely convenient. In debuggers and also disassemblers, learning to use the key presses is a big step forward, because you have to get, just like any other serious product like Photoshop or Microsoft Word, you really have to learn the shortcuts if you want to use it efficiently. So the disassembler window on the left shows the instructions. It shows the address of the instructions, the mnemonic for the instructions, the assembly language version, and then the raw hexadecimal bytes of the instructions. You can see how big it is. All right, then you have the registers in your processor, EAX and EBX, and the stack pointer and the base pointer, which tells you the top and bottom of the current frame, and the EIP down here that tells you the address of the next instruction to be executed. They're in red because they're important. Those are what you want to look at if you're trying to understand exactly what happens command by command. This is the stack. So you'll see up here ESP is FHC, and that should match. Let me see. It looks like it's not quite ESP, EBP, F94. Here's F94, 90HC. Yep, that's it. ESP is HC and 94. The stack is these 3 bytes right here. So those are three words, 32-bit words, and so you see the raw value here. You see it as ASCII text there, which is usually meaningless, and here it tells you what it means, and this one is the return to kernel. So it's about to return to some kernel routine from in there, and if you're in a series of subroutines, where I've called a subroutine, another subroutine, another subroutine, you'll see the return addresses lined up on the stack. All right. And here's a place where you can just dump any memory region you want, and it will just show it to you with addresses, hexadecimal, raw data, and ASCII. So you can dump any region you want just to examine it down there. All right. You can modify data with the spacebar in the disassembler. We did that last time to replace some of the assembly code with different assembly code instructions, typically to do something like nop out some commands you want to skip. You can right-click and modify data in the stack or the registers, and you can edit data in the memory dump. So it's pretty nice, different in the different panes, but you can modify it. Now, when a program loads, it loads into memory as sections. And as we're going to talk a lot in this course, you have various sections of your program. Here's the Labo 901, one of the malware samples that comes with the book, and you see it has a PE header, which is just metadata about how this thing lays out, and then it has the text data section, the R data section, and the data section. The text section contains executable code, and the R data section contains imports, and that contains other data like fixed strings, icons it might use, and whatever other data the program needs. And over here, you can see how big the section is and where it's loaded into memory. Typical programs load at 400,000 if you don't have address space layout randomization turned on. And then over here, you see the permissions. So this is read only, this is read and execute, this is read and write. When you load a program, you call a Windows API call and specify I want to reserve a block of memory this big and I want to give it these permissions. And we'll talk quite a lot more about that as we go ahead. So you can see the layout of all the memory here, all the memory sections used, and there's a lot of them. There's the ones that come directly from your executable, and then all the libraries you use also have to be in memory, so they're somewhere. And you can dump any of these sections by right-click and put them in a memory dump, or double-click them, and see what's in there. Now, a lot of modules have a memory location they would like to load at. That's where they were written to be run at a certain memory location. But now, as a result of buffer overflow attacks, of the type we're doing a lot in the CNIT 127 attack, there's now a defense called address space layout randomization, which is what way all modern operating systems and all modern development environments work. Your code is relocatable, so your code can be relocated to any address in memory, and every time you relaunch a program, it picks a random address and puts it there, just to make it more difficult for an attacker to exploit it with a simple attack. And so the preferred address is at the image base. Most EXEs would like to be at 400,000. That's a hexadecimal number, so it's not really 400,000, but it looks like 400,000. And they relocate to a random location. So their base address would be here, but they're really somewhere else, and then they have a virtual memory address for inside the program. They think they're at 400,000, but they're not. DLLs are more commonly relocated, even more than EXEs, because you might import many DLLs, and if you use several libraries in your program, they each have to load into a different memory section. So if you try to see what this does to the Twitch. Okay. Anyway, so if I imported two DLLs and they had the same base address, they couldn't both load in the base address. One of them would have to relocate. Windows DLLs are smart enough to put a different base address on each DLL to avoid that, but third-party DLLs are often not that smart and will have multiple DLLs that try to load at the same address, so they have to be relocated. So if that happens, if you have code like this, where I'm going to move something to an address relative to a register, then if the register is removed, this would still work. But if you have a command like this that's going to jump to a specific location, 40120, then that's not going to work if the whole program moves in memory. It's got to jump to that 40120, and that address has to be right here. So what you're going to have to do when you move code like this is you're going to have to keep a list of all these locations where they're absolute references and then change them all every time you relocate it. So that's what happens in the relocation section. When you make a library and compile it, it will create typically a relocation section for this reason, and that's a list of all the instructions that have to be changed. So now that'll take more time to load. It'll have to load it, figure out it can't put it where it needs to put it where it needs to be, and then change all these addresses going through the list to make it run in that new location. So here, for example, is one of the DLLs I found on one of my machines, device metaparsers.dll. And when you load it in PEID, for example, you can see the sections. So here you see it's got text, data, and resource, and it's got a relocation section. So that's where it is. That's the list of all those addresses that have to be fixed when it relocates. All right, that's called rebasing. Now you could remove the relocation section of a DLL, and then it cannot be relocated. It can only run at its preferred base address. So if you tried to load a program and it couldn't load at the return base address, you'd get some kind of error. All right, like I say, Microsoft knows that relocating DLLs is a performance waste, so they use different addresses for each DLL. So their DLLs will not collide so often. But, it's not a big deal. So here's what happens if you have DLL A and DLL B. This is a memory map from Olly. And so here's DLL A. They both wanted to be at this address, 100 million or something like that. So this one loaded first DLL A and got the address. DLL B had to load at this other address instead, and therefore DLL B would have had to go through this relocation process, which would waste some time. All right. Now, IDA Pro, this is one thing that's very annoying. IDA Pro is a disassembler and not a debugger, and we're going to start using it next week or the week after. And IDA Pro analyzes the code the way it was written, not the way it's really going to load and run. It doesn't rebase. It doesn't really run the program. So that means if you run OllyDbg on a program, and then you decide to run IdaPro on the same program, you'll get different memory addresses, which can be annoying. There is a manual load option in IdaPro to move its address up to where OllyDbg expects it to be, and you can also remove the flag from a compiled exe so it does not relocate in memory to turn off the address space layout randomization, and we'll do that too in the projects. You'll see how to use ways to avoid this memory confusion from happening. All right, now programs are now multi-threaded. So that the reason you break a program into threads is so that if one part of it is waiting for something slow, like user input or network traffic, the other parts of it can keep moving. So you'll see multiple threads. You can view them in Olly, and you'll see all these different threads at different places. And you could open them in a CPU or kill them thread by thread. I don't think we have any projects in this class where you really have to mess with individual threads, but it is a thing to be aware of, that programs in fact do not just run as one line of instructions, but multiple parallel lines of instructions that can move forward independently to some extent. And each thread has its own stack, its own memory location. So anyway, it can be quite complicated for big complicated programs, but we're mostly going to do simple programs where we don't have these complications. I learned this just a couple days ago when we did the news. Elizabeth came in with this article that said all exploit developers know since 2017 that address space layout randomization is useless and we need to invent a new defense. And I'm like, wait, I don't know that. I'm teaching exploit development, so I'm looking into this. Evidently, there's something I need to learn. They say ASLR is fundamentally shot. And one of the problems is the Spectre and Meltdown vulnerabilities, which are hardware defects in all modern processors. Apparently there are ways to use those defects to find out where you are. So even when you randomly relocate, it leaks out information, which is news to me. So I would love to see how that works and add some projects to the exploit development class where we defeat ASLR with that. But evidently people are just giving up on ASLR, saying there's a hardware flaw which makes it so that you really can't count on those random addresses to stay secret anymore, and we're going to have to add some other kind of defense to these memory sections to stop the attacks. But anyway, it certainly works on the older style version of attacks. But this is what happens to everything. If you invent a new attack, in fact, if you submit a paper to DEF CON, they will say, if you have an attack, talk about what the defense is, and then talk about what the better attack that gets through that defense is. And if you have a defense, talk about what attack will get through it, and then what better defense will stop that, because that's just the way it is. The cops get bigger guns, and the crooks get bigger guns, and the cops get bigger guns, and on you go. And nothing is ever perfect. So every time you learn a great attack, pretty soon they've blocked it. And every time you learn a great defense, pretty soon the bad guys are getting through it. That's just the way it is. Yeah, it's a vicious cycle. This is the cycle of progress, right? We move forward. Our ancestors had a short lifespan and no medicine, and we got clean food and clean water and medicine, and yet we still die. And whatever it is, each generation is like trying to improve from where we are. Anyway, so you can, F9 runs a program. F7 goes forward one step, stepping into subroutines. F8 moves one step at the current level, so if it has a call statement, it will jump into wherever it's calling and finish that and come back without stopping. That's run, step into, and step over. You also have execute till return, execute till user code, and run to selection. You can click on a line in assembly code and run to that. You can also pause a running program. I almost never use this because, of course, programs execute millions of instructions per second, so I don't really know how I could hit a button and pause it at a useful point, but I suppose you might be able to do it in like a video game. Get to the hard place, point it, and then pause it, and then look at the code, something like that. But anyway, those are the various code execution options, and they all have hotkeys. So you can run a program and pause it, but like I say, that's pretty sloppy, because programs run pretty fast. What's a lot better is to set a breakpoint. If you've hit an infinite loop, yes, that's a good point. If it's just running around forever, then you do that. I've gotten a lot of good out of single steps. I've even done single steps. I've even programmed hundreds of single steps per key press and stuff to try to like find things when doing tough problems. Anyway, so you can run. This will just resume execution after hitting a breakpoint. Run to selection is just sort of a temporary breakpoint. You just click on the line and run to the line. Then you don't have to bother setting a breakpoint and removing it. Execute until this function returns. Execute until you hit user code, so you don't stay in library code. This is very handy. I think I never remember it when I need it, but certainly I frequently end up stuck in library code or kernel code, and I just want to get out, because unless you're very advanced, you probably don't really expect to find a bug in Microsoft Windows libraries or Microsoft Windows kernels. I'm usually trying to analyze user code, which is lower quality and more likely to have the interesting bugs I'm looking for. Anyway, and I talked about these: step into, step over. If you do step over, you might miss the most important part if the malware author has managed to confuse you, and what looks like a call to some uninteresting subroutine in fact goes somewhere you wouldn't expect. So, step over does, of course, skip through some things. That's why sometimes I just use a lot of single steps instead. But first you try the easiest procedure, and then when it fails, you go back and try the more difficult ones. That's the general philosophy of all malware analysis. First you do whatever's convenient. The same thing is true of detectives investigating crimes. First you do the obvious, simple thing, and then you don't waste a lot of energy on the stuff where that works. You find the part where the simple thing didn't work, and then you focus on that. So let me bring up the Cahoots. Which is 9A. Yep, good. A. Oh, I forgot to run Zoom. I don't suppose it matters really, but I'll run it later. All right. All right, I guess that's it. All right, so what key press sets a breakpoint? All right, that's F2. All right, how about modifying a line of assembly code? That's the space bar. Good. All right, how about stepping over? Okay, that's F8. All right, and how about I run until user code? Yeah, it's Alt F9, good. Now, I know what you mean, Oblivia. I'm feeling pretty good today, but yesterday I was sort of worn out, I think from the vaccine. I'm glad I got it, though. Anyway. All right. Okay. I know who Uti is. And Sid might be a real name. That looks like a real name, too. All right. And, yeah, well, actually, I got a lot of students that don't like tests, and so you can just do more hands-on projects instead. That's one thing a lot of people would prefer. Anyway, all right. So now, breakpoints, we've talked about them in general already. You got software, hardware, conditional, and breakpoints on memory. A couple of these are strangely simulated by Olly. So the normal kind is just F2, and you can view them with, you can get a breakpoints window that lists all your breakpoints, or you can just see them here as red in the toolbar. Those are the ordinary breakpoints you've added to code. Software execution breakpoints, the most common type with F2. So that's mostly what you do is F2 turns them on, F2 turns them off. There are these exotic kinds I've almost never used, but they're available if you have a more complicated situation than just knowing what line of code you want to stop at. So you can say, by the way, here's something true of Olly and also true of IDA. If you start analyzing a file and you stop, it saves it, and when you open it up again, it has all your previous analysis in there, including your breakpoints. So that can be pretty confusing. All right, so the software breakpoints are useful for a common situation, like, for example, you've got some string you find, but the string is encoded. So you can't read it, and you want to know what it says, so you find your code that calls some routine called string decoder, and so then what you do is you put a breakpoint in, say right after this. So after it calls the decoder and returns, you put a breakpoint, and then someplace, like EAX might point to it, you'll find the decoded string. So that's the kind of thing you do. You can pretty much tell where to put the breakpoint, and you just stop when you hit that line, and you'll find the information you need. All right. Fair enough, so that'll be on the stack here. All right. So for example, a more complicated situation is like Poison Ivy. Now, Poison Ivy was a rootkit backdoor used a lot in the days of Windows XP. And what it did was it would load shellcode that it received from the server. So it would reserve some memory and then load code off a network connection, stick it in that memory location, and then run it. And what you'd really like to know is the code it put in that memory. So it does that by just calling one of the virtual alloc, which is one of the Microsoft API calls that reserves memory. So you could break every time you call virtual alloc, but virtual alloc is called a lot to reserve memory for this, reserve memory for that. So you'd have to keep resuming over and over till you hit the good one. But what would be more interesting would be to set a stack, put a breakpoint on virtual alloc that checks to see the size of the location it's allocated and sees if it's big enough, because shellcode needs at least 100 bytes typically. So that's what they say here. You can make a conditional breakpoint where it will break only if the stack pointer plus 8 is greater than 100. That means the local stack is bigger. That's more than 100 bytes it's reserving. So that's a way to not waste your time on the small calls, and that's called the conditional breakpoint. Now, of course, the way the disassembler implements it is by putting in a normal breakpoint and then breaking every time and then doing the math to see if this condition is true and then just resuming if it isn't. So it still slows down your code somewhat, but at least it just automatically presses F9 for you every time this condition is not true, so it's better than having to do it by hand. All right, and then there's the hardware breakpoints we talked about that are built into the processor itself for debugging code. There's only 4 of them. But you can put a hardware breakpoint, and then if it tries to execute code at that location, it will stop. So it's nice, and this is useful if you have to debug something and the malware uses anti-debugging to notice if it's in a debugger and foul you up. it'd be harder for it to detect it's in a hardware debugger. And as we'll talk about later, there's even an extension you can put in Olly to try to hide the fact that it's a debugger. Anyway, then there are memory breakpoints. This code will break when you have access to a certain memory location. So you might have some string or something, and like a password in string, and I want to find what code uses that password, and I don't know where the address of the instruction is, so I'll just put a memory breakpoint on anytime anybody tries to read this location in memory, then stop. That's the sort of thing. All right, so you can only set one memory breakpoint at a time, and this is something Olly simulates. It's not something built into the processor, and it's not easy to do. It does something like changing the attribute of the memory block to create, I think, exceptions when it accesses that memory, and then continue through the exceptions. So it's got overhead and it's not too reliable. So, you know, it's a little bit imperfect, but it might be good in special situations. And, you know, for example, if you want to know when a library is used, you could find the text section of the library, that's where all the executable code is, and put a memory breakpoint on it, and then anytime any of the instructions in that region is used, it will break. And you'll know when somebody's trying to use that library, so that'd be a good case for it. All right, so let's try another Kahoot. 9B. Looks like that's it. All right, what's the most common breakpoint? That's it, software breakpoint? All right. All right, what kind is limited to just one? The breakpoint on memory, you can only have one of them. All right. All right, and what kind can let you have only 4? Those are hardware breakpoints. Good. All right. All right. That's well. All right. Right. Good. All right, and I think we can just do the next section, and then we'll take a break before the demonstrations, because I've got a nice demonstration. It'll take some time today. So let's go here. All right, so if you want to load a DIL, you can go into your Olly and just browse to a DIL and open it, and that will use the loaddill.exe to load it. That's just a program that will load the library. Now, when you load a library, the first thing a library does is run this routine inside there called DIL main. DIL main prepares the library for use. So, by the way, in the 127 class where we're making malware, we use Metasploit, and that makes libraries that will run malicious things right when they load. So you don't even need to call the functions in the library. You just need to load it, and that will run the malware. So if you put it in Olly, it'll break before it runs, and you have to hit play to run DIL main. Otherwise, that DIL won't be ready to use. And we'll see that in a demonstration later. All right. In fact, I guess I'm ready to do one of these now. So in Windows 2016 Server, which I've got right here, I want to open ws232.dil. And by the way, if you're on a 64-bit system, this is, again, one of the fundamental rules of Microsoft is everything is always named the opposite of what it is. So the thing that is in syswow64, the thing that is in C Windows System 32 is 64-bit code. And the stuff that is in C Windows syswow64 is 32-bit code. Because remember, everything is always named the opposite of what it is. So if you want to find a 32-bit Windows library, you look in this crazy place. And then you'll find it. So let me put this here, and let's just open it. I should be in my previous area. There's syswow64 ws232. This is a networking library in Windows. And notice, all right, it says single step event. All right, I've loaded it, and it's paused. Now, when the first time I loaded it, it asked me, you can't execute DIL directly, shall I use loaddill.exe? And you say yes. All right, now, if I wanted to use one of the routines, remember this is a library with a whole bunch of things. Well, yeah, but actually what's going on is there's reasons why they name it the other way. See, System 32 is the old name. I think it's called C, anyway, and the syswow is Windows on Windows, which runs on 64 and creates that environment to run 32-bit code. So there are reasons why everything has the wrong name in Microsoft, but it is kind of funny, and that's the way to remember things. Anyway, so if I hit debug, I can hit call DIL export, and then it will show me the various functions available in this DIL. But if I hit it, it just flashes a yellow message down here and fails. And the reason it fails is you have to run DIL main, like I just said. So I have to run it with, say, the run button here. And when I do, it says now initialization of debugged DIL finished. It ran DIL main. That's what all that was. And that exported a bunch of functions. And now if I do debug call DIL export, it's freezing up on me again. So I'm going to do debug restart. Yes. Then run this. Then debug. And now it's not grayed out. So like, beware that you're using hacking tools, there are strange little bugs in it. So I just had to do it twice for some unknown reason. And now that I've exported it, now I have this window and I can see the functions. There's one called accept and bind and close socket and connect. And if you've taken like the Python workshops I teach or anything, these are the standard Berkeley networking libraries. This is the heart of the internet. These are the basic libraries used to make raw sockets to connect to the internet. And that's what's in this ws232 DIL. So we can play with it, and there's a nice simple function here, N2HL. So let me show you how to run a function in a library. You choose a function, like there's one that's very easy to use called network to N2HL. And it tells you this is a pure function. What this function does, remember back when we had the assembly language lecture a couple weeks ago, network addresses are in a certain order, but numbers are in the opposite order, little ended first. So you frequently have to change something from little endian order to big endian order. That's all this does. So it has one parameter right here, and you can put in an address. So I can put in 7F. Let me see how I did it here. I put in, 7F001. I put in the network address. 7F is 127. 7F 00001. There, that is the loopback address, 127.001 in hexadecimal. And so if I want to see how the routine works, I can follow it in the disassembler. And this is the code that will do it. Notice it is ending in C750, and here it is, C750. So this is a really simple routine. All it's doing is rearranging the order of the bytes. So as you can see, that's the whole thing. It's just maybe 10 or 15 assembly language commands. And if I run it here with call, it runs, and so it took 7F001 and it turned it into 1007F. It just rearranged the order of the bytes and puts that in EAX, which is where the return value of functions go. So this is a very simple function, easy to see how it works. And this is how now you can load a library and you can run the functions one by one and feed in the parameters and see how they work. And that's where you get the name debugger. I mean, this is not obviously something you do just for hacking purposes. It's to analyze something. But if you have a function and you don't know what it does, you could load it here out of a library and see what it does. Anyway, so that's the game there. All right, and then you can do tracing. So this records execution information, so you can do a backtrace or call stack trace or run trace. These are ways to track down what code has been doing. So a backtrace is pretty simple. Now you move through the assembler with step over and step into for a while, and OllyDbg is recording your movements like a web browser is, right? If you go to a web browser, you click a link, you click another link, you use a back button. You can go back where you were for a while, and you can do the same thing in Olly. You can use a minus key to go back to the previous instruction, but it won't run the whole thing back. You won't see the previous register values. So let me load that 000 game. It's a good example. I've got that one here. This is the game we looked at last week. So right now, it's paused at some kind of loader to change you from 64 to 32 bits. So if I run it once, I get to the game. Remember this game, launch codes, while you got it. I think my dog figured this out. This is a really simple game. So if I step through this game some, F7, 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 it's now jumped into some kind of library. So I'll hit F8 to get out of this library. It's right, I'm going to have to hit F8 for a while to step over until I make it back up. Okay, I've already wandered somewhere I don't want to be, so I'm going to do debug, restart. Yes, and now I'm going to use F8, so I jump over and don't leave this level. So it's F8, F8, F8. Whoa, shouldn't have done, all right. Even F8 seems to have jumped somewhere. For me, this is rude, so I'm going to try again, debug, restart. And I might just do a few instructions because I don't want to get too stuck. Load effective address, move. Oh, the sys enter, that might do something bad. Yeah, step to user code might be good. F8, F8. Yeah, what is the step to user code? Let's see, it's debug. Execute to user code is Alt F9. That's a good idea. Let's try that. I've never been using that, but that's just because I keep forgetting. So let's use Alt F9 and see what it does. Alt F9. Okay, that went to launch codes. Puts, oh good, that seems to be doing what I want. It's stepping at this level. Good, thank you. So Alt F9 stays at this level, and the scanf is where it freezes because now it's waiting for data from me, launch codes. So anyway, if I wanted to go back from here, I could just go, I think backspace, right? Now let's see. Get to my slides. I'm supposed to, oh, minus key. Okay, let me see if minus does it. Minus, yep, minus goes back. But notice these EAX and ECX and everything are not updating. So it didn't really record everything. But I can go back to see where I came from. However, I can make it record everything by doing a better kind of trace. Now there's a call stack trace, and let's take a look at that. If I view call stack, then I see right now I just am one layer down. The kernel launched my program, and now I'm in there. So I can, however, if I go back to showing my code, which is view CPU, hey. All right, that's weird. Let's make this smaller. Okay. So I don't know why the CPU wouldn't come to the front, but that's all right. I'm going to cope. All right, so here we are. And let's watch how this call stack changes. Now, if I go in, let me see if I can make my stuff fit on the screen better. Okay, so there's my call stack. And now, if I do debug restart, and now I use F7, I should dig down in pretty deep. So F7 will step into, all right, And there we go. So there I was inside some kind of library, and here I am. Now I'm in the NTDIL, and now I'm in a second layer of NTDIL, so I'm 2 layers down. And whenever I hit a return, it'll come back. And so, that's what the call stack is. The call stack is all the returns that are pending to get you back to the where they're all started. So that's all it is. How to find how many layers you are deep in a program. Library calling another library. All right. And so we did this. So we can step into, I did this essentially, step into again, and you can see how the call stack changes, and when you return, it gets smaller again. Is the standard? Yes, the standard trace is on by default. You don't need to do anything. That minus sign will take you back to the previous location. All right. And by the way, if you are in a more complicated program, of course, the call stack can get pretty deep. Here it is, maybe 10 or 15 layers down, but not in that simple game. And this is what you do if you really want to be able to go backwards. You do a run trace. So you highlight code, run trace, and add selection. So let's see how that looks. I do debug, restart. Okay, and I don't need this anymore. Okay, so now I run to get to that code there. So now I should be able to do a run trace. So I can highlight the code in this game, and then right-click. Right-click, run trace, add selection. Right-click, run trace, add selection. Okay, and now if I use, say, Alt F9 again, that was a pretty good one. Was Alt F9? Yep, and notice as it runs that the lines turn red that it's gone through. That means you've got this fancy kind of trace running. And it takes some time. So now it's paused at the scanf. So now, I'm trying to get back to my slides. Okay, so now I can use plus and minus. So now if I notice my registers over here, it just printed a message on the screen saying put in the launch codes. So if I could only get this mouse to work, there we are. See, it has ASCII to launch codes. That's where EAX points because it just called this routine and it printed that message. But if I hit a minus sign, it goes back and it's changing those addresses, see? So it's recorded everything. So I can use minus and plus to play back through the steps and see the values of the registers. So that's pretty cool. But of course, this is pretty expensive. It's using a lot of memory. It's slowing down the program a lot because, the debugger has to keep a lot of information to do this. So you don't want to just do this to the whole program. But you do it for a section of code that you want to get a good look at. That's a run trace. All right. All right, and you can trace into and trace over with these little buttons up here. So you can move into subroutines. All right. And you can trace until a condition hits. So here again, you can specify when a condition to quit the trace if you want to. You're doing something fancy, conditional tracing. And then there's exceptions, which we're going to play quite a bit with in the exploit development class. So when something bad happens, when there's some kind of instruction that the processor cannot complete, then it raises an exception, like a divide by zero or an attempt to execute in a memory region that is not executable, or something like that. So you'll get an exception, and the debugger will always stop it. Now, you can press Shift F7 to step into the exception, step over the exception, or run the exception handler. The same as anything else. So typically what you do is hit Shift F9 to go back into the program and let the program process the exception in case the program actually has an exception handler. In malware analysis, you often ignore exceptions. In exploit development, we exploit them. All right. And if you're a real developer developing code, then of course you care about exceptions because they're what makes your program crash, and you have to handle them. All right, you can also patch code, which we were doing last time. You can just hit a space here or right-click binary, edit, or assembler. You can edit, you can fill things with binary, or you can use assemble to write in instructions. If you want to change the code in the text section, you can fill it with things like zeros, nulls to null something out, or nops, 90s. When you can save the code, we did that before, you have to right-click in the right pane of OllyDbg, pane you made a change in, and then save. You can't make changes in multiple panes and then try to save it. You won't get all your changes. the best thing is save it after every change. Otherwise, it's easy to get very frustrated. Right, and by the way, you can analyze shellcode. If you have like binary shellcode that you got somehow, like in Poison Ivy, we said it just downloads it from some network server, so you might be able to make that network connection and get the shellcode, and you just want to run the shellcode, but you don't have any program around it, you can just copy it into the clipboard and just paste it into RAM, and then run it. You can you take some memory and you can make it full access to make it executable, and then you can run it directly inside the debugger if you like. Of course, it's pretty easy to just do it in C or even Python. There are ways to do it. But anyway, you can do it directly in the debugger. You can just insert binary code and run it. All right. You can also analyze the shellcode. You can move EIP into the location of it, set an origin there, and then you'll see the shellcode in RAM. So you don't need to have an executable that you can load through the normal process to analyze the code. All right. You've got a log. The log shows all the calls that were made to get here, all the libraries that were loaded and everything. So that might be useful if you want to analyze something about how you got here. You can watch the value of an expression, and then it will just keep track of this expression like EIP, so you can see all the values that passes through, which might be good. You can label things. This is more commonly used in disassembly but debugging, but you can add your own labels and comments to things to orient you as you go through a big program. And you can extend the debugger just like you extend your web browser by putting in plugins. So OllyDump we're going to use in some of the projects probably next week, where we dump a memory region to create a new executable file. This is how you manually unpack packed code. You run it until it's unpacked in memory, and then you use OllyDump to dump the memory back into an executable. This is the one that hides the debugger. It makes it more subtle so that hopefully malware will not be able to tell that it's in a debugger. You can control it from the command line, or you have bookmarks where you mark memory locations, and there's a lot of other plugins for all sort of purposes. All right, and you can script your debugging. It's better if you use ImmDbg instead of OllyDbg. Then you can just write Python scripts and call the API. And I haven't done this, but what I have done is write scripts for GDB. And some of the projects we're doing in exploit development class are using those scripts. That's extremely easy. You just take a bunch of debugger commands, put it in a normal text file, and you can run it. And that way I can make automated debugging sessions on my server, which is a very good training tool anyway. And I've used it before to make little movies of how memory changes. That's how I diagnosed a difficult problem with Metasploit shellcode years ago. So being able to write simple scripting language on top of it is very powerful when you have something you need to do over and over again, or some complicated situation that none of those conditional breakpoints or anything are solving. You can just write a script that handles whatever weird thing you're trying to do. All right, so 9C is the last Kahoot. We're done with this one, and we can do this one. Good, people still coming in. Maybe that's enough. I'll give it a few more seconds. I guess that's it. Okay, if you press the minus sign, what happens? All right, that's the backtrace. Good. All right, what lets you step back and see previous register values? Okay, that's the run trace, the one that's expensive. All right, what feature shows you all the functions that are waiting for execution to resume? That's the call stack. Good. All right, and how about all the modules that were loaded before the current one? Yep, that's the log. Good. All right, so let's see. All right, Max. Abacus, I think I know who that is. And Twisted, I know who that is. All right. Good. So I'm going to stop this recording.